So if you missed the class last week, we covered the logarithm rules. So in simple words, we summarize and derive some formula for logarithm. And then you can think of log functions as powers. For example, the first formula is log base bxy is log bx plus log by. And the way we did that is, write out the logarithm as the powers and then use our usual power rule. So b to the power p1 times b to the power p2 is b to the power p1 plus p2, right? And we wrote here p1 is, we set it as log base bx, p2 as log base by. Yeah, so here are x and y, x times y, which is our target value, becomes b to the power of p1, right? So this is p1 is logarithm base bx, just means this line just means b to the power p1 is x, right? And then for the second line, we wrote p2 as log base by as b to the power of p2 is y, right? So this is our second. And so b to the p1 times b to the p2 is this relation. We have it. Yeah. So here, and we observe that so actually the power, if you write the definition, right, so the p1 plus p2 is actually just becomes log base b xy, right? So this relation here, so x and y is equal to b to the power of p1 plus p2, and by logarithm definition, it just because log is, we can view it as the inverse function for exponential, right? So write this exponential in another way, using log, we roll the power here, bring down the power here, p1 plus p2 is equal to log base b xy, and this is exactly, and then we wrote here, replace b to the p1 times b to the p2 here, using, we just simply replace our p1 plus p2 here, right? So we write out p1 plus p2 is log base bx plus log base by, okay? Yeah, so log is a way to, we compute powers, right? All right, and then the second formula is, again, if you missed the class last time, is a like direct derivation from the first one. So then x to the power n is like times x, multiply x for n times, and then plus log base bx for n times, and then have n times the log base bx, right? And then I have the logarithm divide each other is like minus, and we talk about it. It's just like multiply 1 over x, multiply 1 over y, right? And then multiply 1 over y, and then when we bring the power here, it's like y to the power of -1. And then using this second formula again, right, we'll bring the power down. This is just -1 log by, okay? And then ln x is just a log base ex, right? And because no matter what the value of b, so this is my sketch of logarithm function for any b. So whether the b is greater than 1, which is shaping this way, right? Or if b is less than 1, greater than 0, it's shaping this way. So either two, then they will both cross this point 1, 0, right? So we will always cross this point 1 0. um, and then for this log function is y is equal to, right, this is y is equal to log base b x. So if you're gonna plug in, so what is it if you plug in this point 1 0 to the function y is equal to log bx? Think about it, which is x is here 1, right? Yeah, and then 0 is y here. So this is just log base b, any b, 1 is 0. So this always holds true, right? Yeah, so we have this log b1 is 0, and this is so if you wrote the power exponential function, then the corresponding inverse exponential function is just b to the power 0 is 1, right? Yeah, and for any b, so the power 0 gives 1. Yeah, and then the 7 is a log b base b give us 1. Okay, yeah, and then yeah, for formula is the last, maybe the 7th formula that we just talked about, and then I mentioned that it's really important to remember the logarithm shape, like the red one. Yeah, so again, if you missed the last class, the red one is the logarithm base b x when b is greater than 1. Okay, and then for when b is less than 1 but also greater than 0, it's a decreasing, like the logarithm function shape, like this blue function. Okay, and then the rest, I think the proof was okay. Like it's okay if you don't follow the proof. As we mentioned last time, as long as you can know how to utilize this ln derivative, I think it should be fine, right? So ln x is equal to ln x prime is equal to 1 over x, and then of course when you do composition of function, you can go over this, but we already covered this in chain rule, right? So we already go over the hard part of chain rule. This is just giving you the formula like again. Okay, so you can go over this on yourself, and then for let's see how where we went to derivative of exponential function. Okay, yeah, and again, you remember that when we talk about logarithm function, according to different value of b, we have different shape of log function, right? And as the exponential function are inverses of logarithm function, so it is also true that for different value of b give our different shape. This might be already familiar with you, but 1b is, you only need to remember one of them. So maybe like 1b is equal to positive 1, right? It's greater than 1, and then its shape is like this. Okay, and when b is less than 1, so to derive this, you can actually think of when b is less than 1, like b is so then a is equal to 1 over b is positive. Oh, but sorry, you don't have to think about this. I think so far we just know that when b is less than 1, you have like b to the power x is another decreasing shape. Then this is fine. Okay, so b greater than 1 is increasing, and then the other is decreasing. And of course you need to know that just like the logarithm function, it also no matter the b value, also always cross the 0, 1 this point, right? Because logarithm, it always crosses 1, 0, right? And last time we talked about logarithm functions are inverses of exponential functions. So inverses means that x, y, they exchange. So for fixed b, you know, for fixed b, uh, the logarithm function and the exponential function, they are just like flip each other along the y is equal to x function. Yeah. So in simple story is that because they simply obtained by exchanging the the y and x. Okay. Yeah. So um yeah, and this is y is equal to this is also going to infinity. Okay, last time we talked about logarithm function also goes to infinity rather than has asymptotic, so it's not bounded here, okay, by any like constant like horizontal line. Okay, it's still going to go to infinity, although it's like flattening down here. Okay, so this is like y equal to inverse function y equal to log base b x. Okay, because if it right, this same function give us so y is equal to b to the x. The same function give us x is, so the same x here. Okay, so the same function, same x here. This is x is equal to log by, right? And then our log function, if we write it, is y is equal to log base bx, right? So you can see that these two, they just simply exchange the position of x and y, right? Because y is equal to b to the x, equivalently, you wrote, bring the power here. How do you express the power x here? So you write x equal to log base by, right? And then the log function, we can always, so any function, we just, it's accustomed to treat x as the uh, independent variable. So we always write y is equal to log base bx, right? And then you can observe that this is compared to this red curve here. Let me write it in red. And this is exchanging the y and x position, right? So that's why these two graphs, they are symmetric along the y is equal to x, this line, right? Yeah. Yes. So if you ever forget one of them, you can flip it using y is equal to x, right? And then this curve again, I wrote is b greater than 1. Okay. All right. And then use the graph of exponential function to evaluate each limit. Whatever. So as soon as you see this, you identify that b is greater than 1, right? So what is b here? You should guess it. And then b is 2, right? B is 2. So it's greater than 1, right? So you could have roughly a sketch of b, okay? A sketch of b is 2 to the x, right? Yeah, so roughly b to the x look like this. As long as you have is increasing, because we only need a limit, right? And then this is just going to positive infinity, okay? And as long as you have a graph here, and then you can treat any other, b to the x right? As long as b is greater than 1, okay? And then this is going to negative infinity. It's going to, you should first have a guess and then we compare, okay? Right. Yeah, so here is not going to negative infinity anymore, right? I should say this is going to, this actually have a asymptotic limit that is uh that is 0, right? 0, which is the horizontal line. So 2 to the x is going to, when x is going to negative infinity, it's going to asymptotically approaching the horizontal line. Horizontal line is always like y is equal to something, right? So this is y equal to 0. Yeah, make sure you don't write asymptotic line is not x is equal to 0, right? Because the height is the same. So horizontal line, the height is the same. So we always write y is equal to something, right? This is the horizontal line. Is is a let me just say this is a horizontal asymptote. Okay. And then when b is equal to 0.2, and then I guess you know what I want to say is less than 1, right? And then the shape change a little bit. Look like this, right? Yeah, and so you know that. And similarly, when x goes to infinity, it's decreasing to 0, okay? So again, y is equal to 0 is a horizontal asymptote. I don't know how to phrase it. I think it's asymptote line. Yeah. And again, when equal to when x is approaching negative infinity, you can see like it's going to infinity, okay, and positive infinity. Yeah, you can also observe the graph. Yeah. Oh, sorry. It's saying it's horizontal asymptote. Yeah, maybe I can change my words a little bit. Okay. All right. Yeah. So if you already seen this exponential function somewhere, and then it should be not hard for you. And then for the natural number e, this is a new way to define e, is that we define it as a limit of n goes to infinity 1 plus 1 over n to the power of n. Okay, and again, e to the, I guess the way we want to talk about e is that if y is equal to log x, again is log base ex, okay, and also e to the x is the same. I think e is greater than 2 point something, right? So e to the x is still increasing this shape, because this thing is greater than, I think it's greater than 2, okay, if I remember it. So the shape is still this. Yeah. And this is just another way to write it is just letting I'll just write it, let u is equal to 1 over n. So n is going to infinity, then u is equal to 1 over n is going to 0, right? Yeah, this is just another way to write it. So it's good to know. Um, all right, yeah. Let's see. And then it also give you like the exponent, because is actually give you like a natural. E is a natural number, uh, which is a limit of actually the limit of this function form, and then e to the x is also use it as a limit. So this is a proof that let's see. Okay, yeah, this is just showing you this function is u x, but I think it's just good to know. Okay, yeah, it's just good to know. Yeah, and then using the same formula here, it's is a proof giving you that e to the x prime is e to the x. But again, I think I think I think it's fine. You don't have we don't have to remember this proof. Yeah. And then I think differentiate and simplify uh, these should be straightforward, right? And this is again this is like a mini example of chain rule. Okay, I'll just say mini chain rule because uh, so e to the u is du is always e to the u, right? And then this is just so first we write e to the x to the 2. Yeah, so taking the derivative with respect to x to the 2, and then we multiply it 1/2. Okay, yeah, so don't forget about this. And this is just like product rule, right? And this is, yeah, again, like just like u is equal to negative x, right? So if you're familiar, you can directly write it as sorry, this prime, this derivative is e to the negative x, and then times -1. Yeah, as long as you learn this, this is fine. Okay. And then e to the any function fx, I think this is like easy breezy for us because we already know chain rule, so it shouldn't be hard, right? So this is the first part, is the first layer of chain rule, right? Because e to the any because e to the any u and then du, it just it's just itself, e to the u, right? Copy it down, the same thing, copy it down, right? And then so we copy e to the fx and then times fx prime. Okay, yeah, and then this is the same saying a row down over again. Okay, yeah, so this shouldn't be hard. So this is again we okay, the first layer we copy because this is because as e to the x, this function derivative itself is e to the x, so that's why we have d e to the u du is e to the u, right? Right, that's why the first layer of chain rule will just copy the function, right? Exactly, because this e to the x prime is e to the x itself, we just copy it down. Yeah, so exponential is handy, right? So here again, the first layer will just e to the u is e to the u prime, differentiate with respect to u is itself, right? So we would just copy e to the -3x, and then we times the inside of the chain rule, like the u prime is -3, right? So we can directly write it. And again, this yeah, again, e to the u du is e to the u, so I just copy it down. And then what is yeah, and then you should be able to write it yourself, right? And then what is the second? Yeah, I think as we have a very pretty solid understanding of chain rule, so Yeah, so I think it should be not hard for you, right? Okay, this is -1, right? And this should be uh, x to the -2 power, right? And then -2, and then yeah. And then what about this? So then I copy. So it's just a matter of practicing, right? Because these we already learned many times. So e to the u again, first there, e to the u du is gonna be, yeah, so let me write it again, d to the u du, and then du dx, okay? So if some of you forgot, okay? And then e to the u du is always du, right? And then I just copy this du, okay? And then you should write it down because it's very easy to watch, right? Because we did it many times, so it's super easy to watch me. But I just want to make sure that you can do it it's super easy for you, okay? And then this prime, okay? And then you should take maybe maybe take one moment to write this down, okay? Keep deriving it. All right, yeah. And then e to the s squared plus 1, and then times, this is 2, so this is another square root, s squared plus 1. This is another layer of chain rule, right? So this is 2 square root s squared plus 1, and then times 2x, okay? Alright, yeah. So hope it's not hard for you. But if you get a different answer, make sure that you go back to the previous notes and definitely review them, alright? And then for I think these are fine because yeah, this is a sing function. I just call it sing function. I just call it cosh function. I don't know if I pronounce it right. Yeah, I just call it cosh function, okay, or cosh function. I don't know. Yeah, I think it's not so much to present about. Yeah, it just plug it in and brute force calculation, okay? I don't think there's so much to talk about it here. Yeah, the cosh function e to the, these two are both either summation for cosh function, summation e to the x and e to the -x, and then this is e to the x minus e to the -x. I guess it could be interesting to okay, and this is yeah, and I think like I won't expect you to just remember this formula brute force, okay? I think like even if appearing some problem, some exercise in exam, it will tell you the formula cosh function. Like I've never seen just mentioning cosh and then without giving you the formula, okay? Yeah, and then you only need to remember one of them, maybe this one, and then or the other one. You remember other one is a different sign in the middle, okay? Yeah. So maybe just be familiar with one of them, and then you know the other, and maybe we can see the derivative, one of them derivative, okay? Because this is again not so much, yeah, I think not so much interesting uh to worry about. Okay, um yeah, let's see, maybe practice one. But yeah, but again, this is nothing but just the derivative of exponential function, right? So yeah, actually this is, yeah, I guess this would be a piece of cake for you guys, right? Yeah, as e to the negative x, we have minus 1/2 and then times -1, right? Yeah, so as you can see, the lectures are actually become more and more like much easier than before, okay? Yeah, you feel it's much easier. So these should be like more or less similar, okay? Yeah, so I think I'll just skip this, and then oh yeah, I think the last time we talk about, yeah, we kind of just mentioned very quickly that b to the x b to the x derivative is b to the x times this ln b, okay, ln b at the front. Yeah, because it has a change of, yeah, it has a change of base here, so we wrote b to the, yeah, so again the method is that we wrote the b to the x is equal to e to base e to the x and then times ln b. So this we change the base, okay? Yeah, so this is a trick of the proof. But again, the proof should be a way for us to review formula, right? Yeah, so don't worry too much about the proof, I would say. And then if you wrote in here, and then e to the x ln b derivative, and again, the first, so e to the u derivative is always e to the u, okay? So first, because we know how to differentiate e to exponential, okay? And then we always copy e to the u, so e to the x times ln b. And again, the constant, like the parameters in front of x is ln b, right? So we need to multiply ln b, and then that's it. And then the first thing, the first e to the u is actually just our b to the x, b to the x, right? Because we change, in the first line, we change the base to e to the power of something, right? So this part here is just b to the x, okay? Yeah, so just change base, and then we using the derivative of exponential of base e, and then we have our formula. But again, this is similar to the formula of e to the x. We just need to multiply the parameter ln b, okay? Yeah, again, this is nothing but directly just write, you can write it down, right? So this is 3 to the x, and then ln 3, okay? Not like log something 3, but ln 3, because we always use ln, right? Because ln is base e again, right? Because in the proof we use the base e, this formula to prove, right? And then we get this. So we use the derivative of the e to the x, this formula. So we got a ln 3, this parameter, right? So it's important to acknowledge that. And this is just product rule, okay? So if you forgot product rule, so we differentiate the first one, 2x times 2 to the x, and then plus, and then you should write it down, verify it with me, and then x squared, this is 2 to the x times ln 2, okay? So this is comfortable, right? Very, I would say very easy, very comfortable question. And this is again chain rule. The first layer will be this whole thing inside the bracket will be our u, okay? So yeah, but if you're very familiar, you can directly write. So this is like u to the power of 3, okay? So if you are very familiar, you can directly write. So this is 3 times, copy it down, 4 to the x plus x to the 4 square power, right? And then times whatever derivative inside is 4 to the x. Yeah, you should write it down because yeah, this should be direct, right? Ln 4 and then plus 4x 3. It's okay if you wrote it a little bit slower. Yeah, and then I can wait for you a little bit. Okay, yeah, it's all right. Yeah, I think this should be this part should be the similar chain rule, right? Again, because first we differentiate with respect to b to the something, right? B to the something, and then we have this parameter ln b. Ln b again because in the proof we use the derivative of e to the something, e to the x, this formula, okay? And then just multiply it. And then second layer of chain rule is just f prime x, right? So the first layer is this is just d b to the u du, right? Yeah. All right. And our u here is u is just fx, okay? Yeah, u is just fx. All right. Yeah. So we're not afraid of it because we know we know how to compute e to the x derivative, and then we know how to write b to the x derivative, right? It's just b to the x copied down and then times ln b, ln the base, okay? And then let's try to write down this, okay? So if you're you should try to write it down yourself, and then we compare, okay? So if you are not comfortable with this, you can also write u is this. Okay, so definitely take a minute to write it down yourself. Right. Okay. 1, 2. And then write it down, try not to look at the left, okay? Yeah. So first layer is 2 to the u, right? Because even if you're fast, the way to think about it is still step by step, right? Because d 2 to the u du is again we know this is ln 2, right? Ln the base is 2, then times copy down 2 to the u, right? Yeah. So even if you're very familiar with it, even if someone is fast, but the thought process is still this, right? Otherwise, it just becomes a memory game, right? And I don't want you to do memory, right? Yeah, so this ln 2 times 2 to the so if you're a little bit slow, and then that's fine. Okay, that's fine. Because we only want and as long as it's correct, even if you take 1 more minute, that's completely fine. But definitely at this point, because we did it just because we did it so many times. So I want you to definitely be correct. Okay, yeah, so it's okay to be slow. And here, if in the exam you are ever confused about, oh sorry, I should say this derivative. Okay, yeah, okay, I'll just say this derivative. Yeah, sorry, because this item is not equal to this. Okay, yeah, so if you write it in exam, this item without the prime is equal to this. This doesn't make sense. Okay, so this prime. Okay, definitely be careful. I should actually copy it down, right? So in the exam, I'll just lose mark, right? Because this itself does not make sense to be equal to this, right? Okay, so this is a mistake that I made, right? So I could actually copy down. Yeah, so actually the process of writing things down is different than just speaking and watching, right? And then this prime is equal to something. And again, if you want to clarify, just write it down the u, okay? Well, I think it's quite important to identify, even if you're fast, is that you're unconsciously defining a u by yourself, right? Yeah, and then so 10 to the u prime, and then this prime is actually d, and then differentiated with respect to u, right? So this is ln 10 times u, right? Yeah. So it's okay to be slow. It's definitely fine, but definitely, make it correct, right? Yeah, just because we already spent so much time understanding it. So ln 10, so 10 to the u, I copy down u, right? So it's actually just the function itself, okay? And then times this prime, u prime, okay? U prime is just d dx, right? And then the next, I think you're probably okay with directly differentiating with respect to x. Or if you're not ready, you should write another layer to define chain rule, okay? If you're not alright to directly, you're not familiar enough to directly write dx here, you should write it another layer, like define v is equal to e to the x minus this, okay? You should do this if you cannot not directly write this down, okay? Oh, this becomes funny. Alright, so yeah, so you can write down now. I don't know how far you get there, but it's okay to take 2 minutes more, 5 minutes more, but definitely write it down correctly, right? And I think we did something similar as this before, right? So if you're not familiar with this part, u prime, or d this square root d sorry, this should be dx, okay? And then if you're not familiar with this part, you should go back and review, okay? So and write it down directly is this. Okay, and then times the inside the square root. Okay, and again inside the square root, e to the x derivative is still e to the x, and then x squared derivative is 2x. Okay, yeah, all right. Yeah, although directly writing it down seems easy, but if your thought process is incorrect, it's super easy to make a mistake. Okay, so if the process, again, you feel is somehow unfamiliar with the definition, or the steps of chain rule, go back to review. Okay, because even if you think it might look easy to write it down, but it's super easy to make a mistake. Okay, and again, the equation of tangent line, I think we did it many times, right? So just first step, compute derivative, and then plug in the point. This point, we talk about it. Whenever we're given a point, and then it's an equation of plug in, right? So plug in this to our tangent. So which is a slope. Okay. Yeah. And then we can the line equation, right? And then first, let's see, y prime is fx prime, and this is, so we can have 1 times 2 to the negative x plus x times, and then this should be ln, right? So always don't forget it, ln of the base times, copy it down 2 to the negative x, and this is not done yet, right? This is not done yet. We just copy it, this, because this part is d2 to the u du. Okay, this part is d to the u du, and we copy 2 to the negative 2x here, and then don't forget 2x is a chain rule, right? So this is your understanding of chain rule. You should multiply -1. Okay, this part is yeah. So if your, so here is like, if your understanding of chain rule is not solid, and then it's super easy to make a mistake, right? And then here 0, 0 is easy. So at the 0, like the slope is, we just plug in 0, right? So 2 to the negative 0 is going to be, is it 0? No, it is 1, right? So 2 to the, anything 0 is 1, okay? And then the second part is 0, the break bracket is gonna be 0, right? So it's going to be 1 plus 0 is 1. Okay, the slope is 1, and then so you can have, the slope point equation, m times x minus 0, and then y minus 0, okay? Because 0, 0 is our y1 and x1, okay? And then this m is 1. Yeah. And the local extrema, okay? So this is again, I haven't checked your homework yet. But it's the, yeah, like the similar old trick. All right, so first we're gonna differentiate this. It's product rule, right? So it's gonna be 2x, and then copy 2x and copy, and then plus x squared, and then whatever inside you know, this derivative, you should be familiar with it, right? So because e to the u, again, first layer is d. So if you're not, I think it's super common to, it's actually super helpful to break it down, right? So even if you're very confident, but you should, I really recommend you to break things down, okay? Um, because eventually we're not competing, like who is faster, but it's really just solid understanding and definitely get it correct, okay? So e as e to the u du anything is still e to the u. Yeah, so here we just copy it down, right? So exponential base e is very comfortable. We just first layer we just copy down e to the u here, and then negative 2x, okay? Yeah. So this is our y prime, okay? Let's see if we can. It seemed like we couldn't. We couldn't. So we okay. So we can have pick out the e to the negative x squared here and then group them together. So this is 2x, sorry, 2x plus, sorry, a minus 2x cubed, okay? Here, so what do we do now? Local extrema. So first, remember the extrema are, you know, global extrema means global max or global max mean or local max mean, right? Extrema means both global and local max mean, okay? But yeah, it's, so if it doesn't give us like a domain or interval, closed interval, it just going to assume that domain is negative infinity to positive infinity. So globally, yeah, I think it's globally, yeah, I think going to positive negative infinity, I think is fine. And then here we just see if there's locally like finite numbers, okay? So we find the, in order to find the critical values, right? So find critical points or numbers. So just let this y prime is equal to 0, right? So if y prime is equal to 0 is, so e to the negative x squared, so this function can never be 0, right? Is that clear? So this exponential function is never going to be 0. I hope this is clear for you. And then, as a matter of fact, so the 0 should contribute from the polynomial that's after this, right? So I can factor out 2x and then 1 minus x squared, because 1 minus x squared. And then I guess I can further write down 1 minus x squared as 1 minus x and 1 plus x, okay? Yeah, so it has like several zeros. Yeah, so the critical values are possibly, the candidates are here, like 0, and then plus 1, so 0, 1, and then x equal to negative 1, okay? Alright, and then what's next? Okay, and then we are, remember that if we talk about local max, local mean, well, we can, last time we talked about, we can actually keep differentiating it and see the second derivative. Or, yeah, so let me write it down. So to see the second derivative y double prime, or to see the sign. You know, sign means it's positive or negative, like on the left or right of this point, right? On the left or right around this point, around the points x equal to 0, 1, and minus 1, right? So which let me see, which do I wanna? So first, let me always want to have x-axis, and then 0, 1, oh sorry, 0, 1, negative 1, okay? And around these, okay? On the left and on the right. So which approach do we want to have? Let's see. Yeah, maybe the sign of, okay, the sign of y prime, okay? The sign of y prime, left and right around the points. Okay, so maybe we want to try the sign of y prime, because y double prime could be more complications, right? And then let's see. So around say x is equal to -1, right? And then y prime is again, so what is the sign of e to the minus x squared? So e exponential function is always greater than 0, right? So this is always greater than 0, positive sign. And then the next 2x, yeah, be careful, this 1 minus x and 1 plus x, okay? Yeah, 1 minus x, and then 2x is going to be, of course, less than 0, right? And what about 1 minus x? Because x is -1 round. Okay, so first we're gonna see what happened when x is, this is x is equal less than -1, right? The sign of y prime. Okay, again we have very limited space here, so we can just do one of this example. Okay, we can just do the example around y x is equal to -1, and I think it should be pretty clear. So when x is less than -1, so minus negative number is going to be positive anyways. So this is greater than 0. And then 1 plus x, so 1 plus something that's less than 1, so 1 plus x is less than 1 minus 1, right? You just replace x with -1, so this is less than 0, okay? Yeah, again, the inequality is like just like equation deduction, right? So 1 plus x, you just want to use your relation is on the left of 1 minus 1, so it's x less than -1. You just bring it down, so x is less than -1 here, okay? Yeah, and then you just, so 1 plus x is less than 1 minus, so 1 plus -1 is less than 0, right? So this bracket is less than 0. So if you have 1 prime is 1 half greater than 0, less than 0, greater than 0, less than 0, 2 negative, so it's still positive, right? So it's still, the whole thing is greater than 0. Greater than 0 is means y prime greater than 0, so it means it's increasing, right? So I'll just, okay, increasing. Yeah, and then what about on the right? So x is x is greater than -1, right? We just do it manually, right? So it's nothing too complicated, right? So just and then see the the sign of y prime. Okay, so x is greater than -1. I can do it again. Okay, here I can do it again here. Y prime is equal to e to the negative x squared. E to the anything, any function is always going to be greater than 0. And then okay, so let us consider between -1 and 0, right? Because we focus on small intervals, so this is greater than -1, less than 0. So 2x is still gonna be less than 0, right? Yeah, because we consider because we have the candidates of critical values are -1, 0, and 1. Yeah, so we consider like these like pieces of intervals, right? And so if we consider this part, and then it's going to be 2x is going to be less than 0, okay? Yeah, and then 1 minus x. So x is still a negative number, right? So 1 minus any negative number is like, yeah, it's minus a negative number, it's a plus a positive number, so it's definitely greater than 0, right? It's even greater than 1, right? But greater than 0 is enough. And then 1 plus x here, right? So 1 plus x, so 1 plus x is going to be because okay, so x is greater than -1, so I'm plugging this relation, x is greater than -1, okay? So 1 plus x greater than 1 plus -1 is greater than 0. Yeah, and then so we have it here. Okay, so we have it, the whole thing, this bracket is greater than 0. And then so positive, negative, positive, positive. So 1 negative. So this is going to be less than 0, right? Less than 0. So in this part, the shape is going down. Y prime is less than 0. Y prime is negative means the y function is the y graph, right? The red curve is a y graph is going down, okay? Yeah. So we know that -1 is the local max, okay? And then if we can keep and then you can just keep analyzing y is equal to 1 is the same, it's going to be the same thing, okay?